Welcome to our lesson on correlation. So far in previous lessons we've looked at ways for making inferences from two different samples, where we first just compared maybe the average of one sample and the average of another sample. Then we moved on and considered two dependent samples where the data was somehow linked, and so we were talking about paired data. And then we looked at hypothesis testing for claims about the population of the differences between those two. Think of like pre-test and post-test scores all given to the same person. Well, sorry, each pair given to the same person. So you have a bunch of pre and post tests on the same set of people. We also constructed confidence interval estimates of the mean of those differences of, again, those test scores. In this lesson, we're going to continue to consider paired data, where you have two measurements on one item. So something's being measured twice. But no longer is it just a pre and post test score and we look at the differences between those. We're now going to see if there's actually a relationship between all pre-test scores and all post-test scores. So it's a fundamentally different question that we're trying to answer. In this lesson, we're going to introduce methods for determining whether or not there is a correlation, or what you can think of as some sort of association between two variables. We're going to initially look at just if that relationship is considered linear. Later on, we'll see that we can also judge whether or not there's a relationship between them that is not linear. Now, when we're dealing in the linear case, we can also identify an equation that best fits our data, and then that will allow us to predict values of one variable based on information from the other variable that might not be in our sample. And that's a really important tool. So linear regression, as you'll hear, is regressing a line and allowing you to predict. We're also going to look at ways that we can analyze the differences between the predicted values that we're getting out of our model and the actual values that are present in our data, and it'll help to either further justify the correctness of our model or show maybe that it's not that great. It helps to measure its accuracy. Now, in addition to all this, we're also going to consider methods for identifying linear correlations amongst three or more variables, right? We're going to start off with a linear correlation between two variables. We're going to look at ways that we can also look for a linear correlation between three or more variables, and then we're even going to go beyond that and look at ways to find an equation that can relate variables in a nonlinear way, so in a curved fashion. Luckily, we're just going to be kind of looking at those briefly, and we won't have to do a lot of crunching of the numbers, because that can get kind of complicated. Okay, so when dealing with correlation, part one of this lesson is going to introduce the idea of a linear correlation coefficient, which we call R. And R is simply just a number that ranges between -1 and 1, and it measures how well our sample data would fit to a straight line pattern if we graphed it. We're going to be making scatter plots. And if our data all lines up in a nice straight line, then R is going to get closer and closer to either 1 or -1, depending on if it's a positive or negative slope. And if it's all scattered and it's not really good at all, then it's going to be closer to 0. To find this value R, there is a way to do it by hand. I mean, there always are formulas for all these things, but we're absolutely going to let technology do this for us. And then based on the strength of that R, the value of that R, we'll be able to conclude whether or not we think there's a linear correlation between two variables. In the second part of this lesson, we'll also look at methods for running an actual hypothesis test on that correlation. We'll basically just ask the question, is there a correlation between these two variables, yes or no? And then we'll run a hypothesis test to see. So let's start with the basic concepts of correlation. As mentioned before, correlation exists between two variables when one variable is somehow associated with the other, right? A linear correlation exists when that relationship results in a straight line pattern if you were to plot the points out. The best thing to do whenever trying to determine what kind of correlation your data has, the first thing you should always do is just run a scatter plot. So here are some examples. The first scatter plot, you can see that the lines tend to have a linear pattern. I think we can all agree that there's a trend to these lines. Well, it's bad, maybe more like that, but you get the idea, and we can all agree that there's a trend for these, excuse my poor drawing skills, but a straight line in that direction. And so that is why the second set has a negative R, because the negative tells us that there's a negative trend, right? That line would have a negative slope. In other words, as the X variable, remember each dot represents one item that's being measured on two things. You could think of these as heights and weights, right? So you get a bunch of people, X represents their height, Y represents their weight. Obviously this wouldn't make sense because as your height goes up, your weight wouldn't go down. Right, so it would have to be something else, but you get the idea that each dot represents two different measurements. So if that's one person who had this much, right, this dot here had that much of the X quantity, whatever was being measured, and that much of the Y quantity. And according to this pattern, as measures of the X quantity go up, the Y quantity goes down. Over here, however, as the X quantity goes up, the Y quantities also go up, so that's why they have a positive correlation. This next slide shows something that would be considered no correlation at all. It just looks like buckshot. It's just all randomly spread everywhere. And then this one here shows a very strong correlation, right? These things are lined up in an almost perfect pattern of a parabola. It's just not a linear correlation. If we were to run this data and try and find a linear correlation for that data, we would get a really horrible R value, right? Our R is really, really small, which tells us that there's no correlation between the points, but it's testing for a linear correlation. If you tried to draw straight lines anywhere on here, whatever direction you wanted, none of them seem to fit the data very well. And so we're going to get a really bad R. But we can see that there's a really strong nonlinear relationship between this data. We could fit an upside down parabola to it fairly well. Okay, like all of our other tests, we always have requirements before we can run them. In order to run this, our sample data have to be paired, right? There has to be an X and a Y, and each set of X and Y have to come from one item being measured, whether it's people or cities or countries or something's being measured two different ways. It has to be a simple random sample as always. It has to be quantitative data as always, or we can't run these types of things on it. You should always run a visual examination of your scatterplot data to confirm that the points actually have some sort of approximate straight line pattern. When you get something like graph D, as in David, you're going, well, that's not a straight line. There's no point in running correlation. But when you get a C, you could go, well, there doesn't look like there's anything, but I can still run the numbers. A and B, you would obviously see a good pattern and go, this is telling me I most likely have some good correlation. The next thing is, if you have outliers, you must remove them. We've talked about outliers before and decisions to keep them or remove them, but outliers must be removed because they have a huge effect on linear correlation. So we know that outliers have a fairly strong effect on the mean and almost no effect whatsoever on the median, but when it comes to calculating R and your linear correlation, they have an enormous effect. So you really want to eliminate any outliers. Some of the typical notation that we'll see, N is still number of things, right? As always, X is still your variable. This just remember designates a sum. So if you can think back to when we were doing means and standard deviations, we saw these symbols before. These are just all the different things that are going to be in the formulas for calculating these things by hand, but we're going to let technology do most of it for us. Lowercase r just is the correlation coefficient, right, that we're going to get, and then this looks like a P, but it's lowercase rho. Rho, right, R, rho, that's where it comes from. That's the linear correlation coefficient for the population, the thing that we're going to be hypothesizing about with our hypothesis tests. Here is the actual formula if you wanted to try and compute R on your own. And it looks very complicated, but it's really not that bad, right? You're just summing up the products of x and y, summing up the x's, summing up the y's. Right? These are all simple things to do. Summing up the x squareds, summing up the y squareds. Very, very easy. But why do this by hand? Technology is going to do it for us. Interpreting R. When you get an R value, and this is something that is still under debate, what is considered a correlation and what is considered a strong correlation? What's considered a weak correlation? What's considered no correlation? Well, there are tables that give ideas based on your sample size as to how strong or how big R needs to be before it's considered statistically significant. Not everybody agrees with every table. The table that might be in our book might be something that is agreed upon by some and not others. So just keep in mind that if you're determining whether or not R is sufficient, right? Determining whether or not R is strong enough to make the claim that there is a linear correlation, that's still a fairly subjective determination. Also remember that everything we're doing here only applies to linear correlation, right? We're going to start with the very simple linear correlation. We'll touch briefly on nonlinear, but for the most part, we're only going to be talking about linear stuff. When dealing with linear correlation, as I mentioned before, R is always between plus and minus 1. And it can equal 1 and minus 1. And if it does, that means you have a perfect linear positive or a perfect linear negative correlation, which really would only happen if you manipulated the data. You're not going to find that in the real world. You can find things close to it, but I doubt you'd ever find something in the real world that was perfectly linear correlated. If all the values of either variable are converted to a different scale, the value of R does not change. That's really important. So if you were measuring, let's say, the length of your femur bone and your height, we know that those two lengths are very strongly correlated. If you listed the length of your femur bone in inches and then your height in inches and ran the data, and let's say you got an R of 0.92, which actually isn't too far off for that type of data. And then you went back and took your data, and instead of listing the femur bone in inches, you listed it in centimeters and kept the height in inches, right? So you just changed the femur measurements to centimeters but kept the height measurements in inches. You would still get the exact same R. Okay, so your R is not dependent on unit of measure. You can do what are called transformations to other units of measure and it won't change your R. Also, the value of R is not affected by the choice of x and y, which means when we're doing these types of analyses, we're always letting one measurement be the x measurement and one measurement be the y measurement. And we normally choose those in the more logical sense where x is your input and y is your output. Just like in normal kind of function notation, you put something into x and then you get an answer out of y. If we were looking at, let's say, height and weight, right? Which one is really logically dependent on the other? Does your height depend on your weight, or does your weight depend on your height? And we can all agree that it's more logical to let your weight depend on your height, right? As your height goes up, your weight should go up. But in the other sense, as your weight goes up, you don't necessarily get taller, right? There is still a relationship between them in both directions, and therefore R is not going to change depending on which one you let be x and which one you let be y in your calculations. But there is a logical reason to why you would want one to be x and one to be y. And depending on the type of research you're doing, you give these different names. You know, if you're doing strict scientific research, you talk about these as independent and dependent variables. X is the independent variable, the thing that's allowed to change, and then Y is the dependent variable, the thing that depends on the X. But that's normally reserved only for strict scientific measurements. If you're running this type of analyses in a more social science setting where you don't actually have the ability to manipulate the x, you don't have any control over it, you're just observing both the x and y, then instead of calling them independent and dependent, you normally use the terms explanatory right? Or sometimes called the predictor variable. That's the X, explanatory or predictor. And the Y is called the response. So normally it's explanatory and response instead of independent and dependent. But, you know, tomato, tomato. R is always going to measure the strength of a linear relationship, and R is very sensitive to outliers, as I've said before. So you always want to make sure you get rid of those first. Let's look at an example. Here is a very small set of data where we have measured both the shoe print, i.e. the length of someone's shoe, and their height for a bunch of men. And we can use a computer or a calculator to find the value of the correlation coefficient between those two. And wouldn't we expect that there should be some correlation between your height and your shoe size? First things first, we always want to look through our requirement check. You know, the data is a simple random sample, it's quantitative data. The plotted points appear to have a roughly straight line pattern, and there are no obvious outliers, so there's nothing we need to remove. The biggest thing to take away from this is do your plots, right? You always want to do a scatter plot to see what your data looks like. Next thing, we would throw it into technology and get an answer, depending on if you're going to do Minitab in your calculator, StatDisk, StatCrunch. They all are very simple for running linear correlation. You're just looking for an R and a p-value too. We'll need that later, but for now we're just looking for R. You'll notice that with the calculator you don't get a p-value. I think some of the fancier newer versions do give you a p-value, but the older 8384s do not. But you can get a p-value out of technology very simply. But they all do give you the same R, right? So a correlation coefficient of 0.59. Seems strong? Seems weak? I don't know. What do you think, right? It's still a subjective thing. 0.59, it really depends on your opinion as if you think that's a strong correlation or not. Using the formulas, I don't even want to put them here because they're horrible. Just use technology. Okay, is there a correlation? Right, well, we found our R to be 0.59. Now we need to interpret it. I like the p-value method. That's a pretty big P, right? 29%. Because the p-value is not less than our significance level, we conclude that there is not sufficient evidence to support the conclusion that there is a linear correlation. Now you might be asking yourself, well, where did that come from? I don't even remember making any claims. We haven't got there yet, but what we're basically going to do is we're going to run a hypothesis test on R. And when we run our hypothesis test, HO and H1, HO is always that rho equals 0, meaning that there's no correlation. And then H1 is that rho is not equal to 0. And remember, rho is just the population version of R. So we're testing whether or not correlation equals 0. When we get a p-value this big, right? Remember, if p is less than alpha, then you reject the null hypothesis. Well, in this case, p is greater than alpha, so we fail to reject. So we fail to move off of our null. We didn't have enough evidence to reject it in favor of this. So we're left with the null assumption that there really is no correlation. Even though we have an R that is definitely not 0, right? We had an R of 0.591, which some people might consider to be fairly strong. According to the data, it wasn't strong enough to really say that there is a linear correlation. That's my preferred method for deciding whether or not there's a correlation. Some people just look at a set of tabled values and say, hey, if your R is bigger than this, then it's considered significant. And here's that idea. From tables, we're told that for 5 pieces of data and an alpha of 0.05, we would need an R value of plus or minus 0.878, right? They're always going to give you the absolute value version of it. So if you got a negative R, you would just have to take the absolute value of that and compare it to the R from the table. Since R's is smaller than it, right? RR, was 0.591, then this gives us the same result, no correlation. Okay, R squared, or what's called the explained variation, right? R is our linear correlation coefficient. R squared is our coefficient of determination, is what it's normally called. And it is the proportion of the variation in y that is explained by the relationship between x and y. It's the amount of changing, right, variation in our y variable that can be explained by changes in the x variable. Think about trying to predict how much money you're going to make in the future. There are all sorts of variables that will determine how much money you're going to make, let's say at age 30, just to be consistent. Your gender is a factor, right? I mean, that we still have the glass ceiling for women. They normally make about 70% of what men make in the same job. Race is still, unfortunately, a predictor. Obviously, your schooling, right? How much education you have is a predictor. Where you live is a predictor. What field you're going into is a predictor, right? All these different things are going to influence how much money you're going to make at age 30. And so therefore, if we went around and just collected, 1,000 random samples of 30-year-old people and found out how much they made, there's going to be variation, right? There's going to be differences in the y's, the y being each measurement of money for each of those 1,000 people. And some are going to make a lot of money, some are going to make very little money, more people are going to be in the middle. It's going to be all over the place. There's going to be variation, and there's going to be all sorts of things that somehow, you don't want to use the word cause, but somehow relate to that variation. There's going to be reasons why person 1 is making more money than person 2 and is making less money, let's say, than person 3, and etc., etc., etc. Once we decide to test for a relationship between two specific things, remember right now we're just doing linear correlation between two specific things, so we can't look at race and gender and education and location and job, genre of job and all those things. We can't look at all those things at once in these models. We can only look at one thing. So if we're going to try and predict or look for a correlation between money, then maybe we would just look at years of education. How many years of education do you have, right? If you have a high school diploma, that's 12. If you have an AA degree, that would be considered 14, right? 2 years of college. If you had a bachelor's degree, that would be considered 16. 4 years past high school. A master's would be 18, and a PhD would be 20. We could look at all of these people, and obviously we would have to gather all this data. Not only did we get how much money they made, but we also asked them how many years of education they had. We got their race, we got their gender, where they live, what kind of job they're, all this other stuff. But we're only going to look at years of education and salary. Well, R squared, once we run the data and we get an R and we get an R squared out of our technology, let's say it comes back and it gives us R squared equals 0.35, let's just say. Then that means, according to the data, according to the sample that we have, 35% of the variability, right? 35% of the changes in salaries observed in our sample can be somehow attributed or explained by the variability in X, i.e. the years of school. So you could almost think of how many years of schooling you have as being responsible for 35% of the changes in the possible different yearly salaries you might have. Whereas 65% of that variation is caused by other things that aren't in the model. Again, your race, your age, your gender, where you live, what kind of job field you're in, those other things are causing 65% of the variability, right? They have a bigger influence on why you make as much money as you make compared to why somebody else makes as much money as they make. Okay, so that's what explained variation is. It's the proportion, right? The percentage of the change in your y variable that can be somehow explained or attributed to the relationship between x and y, right? The input variable. And when you get more things in your model, so when we start doing what's called multiple regression, where you let more than two things be the input, right, be the x, and you're seeing how they influence y. So now instead of just looking at years of education, you also then factor in age, gender, and race, let's say. Now we have 4 variables. And when we do that, we'll still get an r and we'll still get an r squared, but now that r squared, and let's say that went up. When we put in those 4 variables, now we get an r squared of, let's say, 0.7. We've doubled it. Yay, woo, we've done great, right? But what does that really mean? It just means that those 4 variables combined now can explain 70% of the variability in your salary. There's still 30% unaccounted for by this model. So a lot of times you'll hear that phrase of the proportion of the variation in y that is explained by the model being the things that you're putting in and seeing how the relationship works. We found previously in our other example that r was 0.591, so really all we have to do is square it, right? R and r squared, that's not just a name, that's actually what it is. R is just the square, I'm sorry, r squared is just the square of r. So you take 0.591 in your calculator, square it, you get 0.349, and it turns out that almost 35%, right, 34.9% of the variation in height can be explained by the relationship between the shoe length and heights. And the other 65% is coming from something else outside of the model. Some common errors involved in doing these types of things. You always have to stay away from the word cause and causality and causation. You cannot conclude that correlation implies causality. That's a big, big thing. There are many examples of things that are correlated, but one does not in fact cause the other. A silly example, and this is a true thing, if you were to go around and look at the data, look at the numbers, the amount of ice cream sales and homicide rates are strongly correlated. And what that means is as ice cream sales go up, so do homicide rates. As ice cream sales go down, so do homicide rates. So does that mean ice cream sales somehow cause homicides, right? The more ice cream you sell, the more people get murdered? No, that's silly. We all know that can't be true. What's happening is there's what's called a confounding variable or a lurking variable in there that we're not thinking of that's actually causing both of those things to happen in tandem. Both ice cream sales and homicide rates are going up because of something else, right? There's something else that's influencing them. And that happens to be the weather. It gets hotter outside, people buy more ice cream, they also get more agitated, and they go and shoot their neighbor. So that's really more of where the correlation is. It's still not a causality, right? Hot weather doesn't cause homicides. It's not a direct cause, but there is a correlation. When you see on the side of a pack of cigarettes that it says smoking causes cancer, that's because they've actually run rigorous scientific experiments to show not only a correlation but in fact a causation where smoking does in fact cause cancer. It's kind of like saying stabbing causes bleeding, right? We can actually prove that it causes bleeding, and there's actually a correlation between amount of stabs and amount of bleeding, right? But that is something that you can actually show as a causation. Everything else you can only show there's a relationship, there's only a correlation. So avoid ever trying to say something causes something. Another big problem when people run regression and correlation is if you use averages. Well, averages suppress variation, right? Instead of looking at all the different possible outcomes, you're looking at an average of a set. So you've ironed things out. You no longer have big values and small values, you just have the middle value, right? The average of everything. And because you've gotten rid of all that variability, you will often get results that are much stronger than they would be had you looked at the original set of data. So if you're trying to correlate one set of measurements to another set of measurements, and those are both averages, so you're now looking for a correlation between averages and averages, you're going to get a very strong correlation that might not actually be there. So using averages will inflate your correlation coefficient. It'll make your R closer to 1 or -1. And the last thing to remember is that we're dealing with linearity. There might be a very strong relationship between your two variables. It just might not be linear. And the best way to see that is to always graph your data, right? The first thing you always do is run a simple scatter plot to see what kind of trend you can see. Can't be said enough, which is why I'm going to give it its own slide. Correlation does not imply causality. That's the biggest thing. Okay, on to the formal hypothesis test that we can run when we do these linear regressions. Some more notation. N is still the N we're used to, R is still the R, and rho is still the rho. So nothing new there. Requirements, just like before, simple random sample, have to be paired. You want to run a scatter plot to see that the pattern, right, is somehow conforming to a straight line pattern, and you want to get rid of all of your outliers. So nothing new there as well. As I've stated before, here are your simple hypotheses. The null is always that rho equals 0, meaning that there is no linear correlation, and the alternative is always that rho is not equal to 0. So as before, we're normally trying to reject the null. As with most hypothesis testing, our goal is usually to reject the null. And we're innocent until proven guilty, right? We need enough evidence to prove guilt. We need enough evidence to reject that initial hypothesis of innocence, right? So we're trying to get enough evidence to move off of the null in favor of the alternative, right? So we want to reject that null. We're still going to use either the critical value or the p-value method. I prefer the p-value method as always. The hypothesis test for correlation is basically just asking, if R is sufficiently far enough away from 0. We're almost never going to get a 0, right? So you would kind of think that the answer should always be reject the null, because we're never going to get an R of 0. But that's not it. Remember, just like when we run other hypothesis testing where we're testing for something as simple as the null would be that mu equals 20, right? That the average of the population equals 20, and our sample mean comes back as 22, and you go, well, shouldn't I reject right off the bat? But remember, just because it's different doesn't mean we reject. It has to be significantly different. So same thing here, right? It has to be significantly different. So we can get critical values from tables. We can get p-values from technology. Either way, it's still the same idea. In our previous example, we found that R was 0.591. We can conduct a formal hypothesis test of the claim that there is a linear correlation between the two variables. So if our claim is that there is a linear correlation, and we're going to use 0.05 as a significance level, but if the claim is that there is a correlation between the two, then which of our two hypotheses is our claim? That one. Right? That's the one that there is a linear correlation. So the alternative becomes our claim, which, as we've stated before, is always the better of the two ways to go because it's the stronger argument to test. With an R of 0.59 and the critical values that we found of 0.87, we see that we fail to reject. Also, with an alpha of 0.05, and if you don't remember, but previously when we looked at it in technology, the p-value that we got, I believe, was around 28 or something like that, 20 something, which was definitely bigger than 5%. So we also would fail to reject at that point, and we would have to conclude that there is no linear relationship between your shoe size and your height. When we're running these hypothesis testing, we're actually running them on a t-distribution. And so we're getting t's as our test statistic. This is the formula for our test statistic. It's actually very simple and something you could do by hand very easily, but it's easier just to let technology do it. Because now that you have this t-value, you'd still have to go look it up in a table, right? You'd have to use n-2 as your degrees of freedom, and not all tables have all values, so you'd have to approximate your p-values, and that can be a problem, so just let technology do it for you. If we want to do this by hand, that would be the t-value we would get. If we look that up in a table, that would be our p-value we would get, and hey, my memory's not so bad. I thought it was somewhere around 0.29. But just like before, because that's bigger than 0.05, we would fail to reject. So in either case, we get the same conclusion. Now, in this example we ran, we were doing a two-tailed test, right? We were claiming that the claim was that there was a correlation, so that rho was just not equal to 0. But you can actually make the stronger claim of a positive or a negative correlation, right? Rho is less than 0 for a negative correlation or greater than 0 for a positive correlation. And you can still run these tests the same way as you would normally. It's just now you're running a one-tailed instead of a two-tailed. Now what if we did want to run this with technology? Let's look at how simple it is to do it in the calculator. Here's our data as we saw before. The first thing you would have to do is put these into two lists. List 1 is supposed to be your X and list 2 is supposed to be your Y. You could put them in any list you want, but if you put them in 1 and 2, it just makes your life easier. So I've already put the data in here. Next thing you want to do is go to tests and run linear regression t-test. You see how it asks for where your X and Y are. So you could change these if you didn't have them in list 1 and list 2, but if they're in list 1 and list 2, you can just ignore that and go on through it. Frequency, that's only if you had a weighted table where you had a table of weights, you could put that frequency in another list. Just leave it alone. Okay, here is your hypotheses. Are we hypothesizing that rho is not equal to 0, right, or less than or greater than? So if we wanted to do a one-tailed test, we would just highlight those. Reg equation, this is a very cool thing, where if you tell it a y value, it will populate your y equals, this screen, with your reg equation. So back here on this screen, go down to reg equation, hit variables, y variables, right, function variables, and just choose one. I'm just going to choose y1, hit enter, and now it's going to put my regression equation in that first thing. Hit enter and it computes everything for you. Now I misspoke earlier when I said the calculator won't give you p-values. That's if you just run linear regression. If you run linear regression t-test, it will in fact give you p-values. You'll see that here is our test statistic. There's the t that we just got of 1.127 if we round, right? There's the p-value of 0.29, so we would know to fail to reject. Degrees of freedom, there's our A and our B, right? That A and B is from up here. It's giving us the equation of our linear regression line of A plus BX. It also gives us some extra stuff. It gives us S, there's our R and our R squared, right? So everything we need to know. Now here's the really cool thing. If you look at Y1, this is my regression equation from the other thing. There's the A plus BX, right? And if you go to stat plot, turn your first plot on, right? So I'm going to turn my stat plots on, and I want to do an actual scatter plot. I want to do it on list 1 and list 2, right? So that's all set up the way I want it to. Hit graph, and you don't really see anything because it's not set right. So you want to zoom down here to zoom stat, and now it sets it for a scatter plot. And you'll notice that line is the actual regression line. If we didn't have this here, right, so we can turn this off and then graph, there's our scatter plot of our 5 pieces of data, and we can see, yeah, it kind of looks linear, right? That's the first thing we should always do, is check that. But then now that we have this line, this regression line that the technology did for us, now we can see that's where the regression line fits on our data. It's a pretty cool tool on your calculator to show you how this works. Okay, what about in StatCrunch? Rather than deal with our simplistic little example of only 5 pieces of data, I thought I would open up a large data set that I have on some bears, right? And we've got all sorts of measurements here. This is the width of their head, this is the length of their head, this is, I believe, the length of their body, this is the measurement around their chest, all sorts of great things. So now we can run stat regression, right? We're doing correlation, which is part of regression, and then here's all of our choices: simple linear, polynomial, multilinear, logistic, right? All sorts of really cool stuff. We're just going to do simple linear. Then we have to tell it what is the x and what is the y. So I'm going to choose my X. My input is going to be, how about the size of their chest, right? The circumference of their chest, and see how that relates to their overall length. And then we're going to run a hypothesis test. We could change our hypothesis intercept of 0. That means that means if you had a 0 chest length, right, or chest circumference, you would also have a 0 length, which makes sense. A bear with no chest would also have no length. And then slope, that's your row, right? A 0 slope means no correlation, just means a straight flat line. There's all sorts of extra stuff you can do in here that you don't have to worry about as far as predictions, fitted lines, right? We want to put the fitted line plot that'll show us the regression line. We can save all sorts of things to our table over here, but don't worry about that. Just leave all those basics there and do compute. Here is your test statistic. Here is my p-value, right? So with a p-value that small, it definitely means that there is a correlation. And in fact, my r is pretty darn big. My r squared is also pretty darn big. And if you click this little next button down here, there's my graph. Scatter plot with the fitted line. Okay, and if we had run it on those same 5 pairs of data from the shoe, and we would have got something that looked just like the one on our calculator. But I just want to show you how to do it in StatCrunch. It's very simple, it's very easy, and of course you can copy, right? Copy these things, right click, copy the image, and then paste it straight into a Word document or something like that if you need it. Alright guys, that's everything you need for correlation.